Question 1 looks at isolation, and it says you've used a multifunction test instrument set on voltage scale. So you're measuring the voltage and you inadvertently measured it across the terminals of an open control switch. Now if we're going to test isolation, we don't want to go across switches, we want to be across the load or where we're going to disconnect it. And if you go across a switch that may be open circuit somewhere within that control circuit, you're going to get a 0 volt reading, even though the oven may still be live. So we can't trust any voltage readings across a switch. Why a fuse is not installed in the secondary of a CT, a current transformer? Well, current transformer is very dangerous if the secondary is open circuited, so it should always be connected. And so if we put a fuse in there and that fuse blows, then we could get dangerously high voltages across the CT windings. Fluorescent fittings installed in final subcircuits across 3 phases in a factory. 2 methods of reducing the stroboscopic effect. So the stroboscopic effect, if they flash at the same rate as the machinery is turning, it may make the machinery look as if it's stationary. Someone could put their hand in there. So how do we make sure that doesn't happen? If we've got double tube fittings, then we could put a capacitor in series with one of the ballasts, and then that would put the 2 currents out of phase. Or we could have lead lag fittings, which is basically what this is. We could put the fittings on different phases, so they're peaking at different times. Or we could put some incandescent lighting with the fluorescent fittings. So the incandescent lighting will give a continuous light, whereas the fluorescent fittings will give us the 100 Hertz, or the 100 Hertz flickering. The sensitivity of a RCD, so that's all about the current that's required for it to trip, the imbalance required for it to trip. And for one that's in a patient treatment area, we can't have any more than 10 milliamps. So the sensitivity of a patient treatment area RCD is going to be higher than one that's just for personal use or in a domestic installation. An electrician is using a voltmeter test for isolation on a 3-phase isolator. They've proved their meter, they've tested, but they've only tested between each phase, and then they've proved their meter again, and when they dismantle the isolator they get electric shock. Well, the testing wasn't effective because they didn't do the test between phase and earth or between phase and neutral. They just tested between the windings. It's not good enough. You need to do all those tests. You need to make sure there's no phase to earth voltage and no phase to neutral. 3-phase motor, 6 terminals and 3 windings, rated at 230 volts. How are we going to connect this to a 400 volt supply? Well, as soon as we see 230, we know it has to be in star, because across the star winding there's going to be 230 volts. Why are 3-phase motors smoother and quieter than single phase? So we've seen this question before. They have a rotating magnetic field that's constant. So a constant rotating magnetic field. Why a run capacitor would be fitted to a single phase split phase induction motor? So it's in the run winding, so it's nothing to do with starting. So once it's running, if we've got a capacitor in there, we're going to get quieter running, better running torque, less current drawn, or increased efficiency. So it's looking for 2 of those. And I would be remembering that it's quiet and we get a better running torque. A capacitor in the start winding gives us a better starting torque. 2 components typically used to smooth DC of output of a rectifier. Again, we've seen this question before. Capacitors and inductors are the 2 that I would remember. They've given us a number there. I would argue a lot of these are about regulation rather than smoothing, but they'll accept them for smoothing. But capacitors and inductors are our 2 main methods of smoothing DC. Inverse time current characteristic. Again, we've seen this before, and it's all about The bigger the current that flows through a protective device, the quicker that it's going to operate. So as the current through the protective device increases, the time taken to operate decreases. So it's inversely proportional. 2-core MIMS cable to be reconnected to a single-phase fuel pump. 2 important mechanical precautions. So it's looking at things like avoid damage to the metal sheath, maintain the loop or S-bend in the cable, do not disturb the pot seal, do not overflex the solid conductors, ensure the gland is clean and tight, and the connections must be tight. So it's all about making that gland assembly waterproof, making sure it's all nice and tight, and making sure there's no damage to the metal sheath. Draw and label the circuit diagram of a glow start single tube fluorescent light fitting. So here's our diagram there. We've got our phase and fuse feeding the ballast or the choke. It feeds one end of the tube through the starter, through the other end of the tube, back to the neutral. And we've got a power factor correction capacitor there and a radio interference suppressor capacitor there. Describe the starting sequence. So how do we start this thing? So when we first turn on, the bimetallic strip within the glow starter is closed, and so we get current flow through the choke, through the ends of the tubes, through that starter, through the other end back to the neutral, and so these start to warm up and they ionize the gas around the electrodes. Inside here, this gas is heating up and this bimetallic strip is opening, and when that bimetallic strip opens, the supply is taken from this ballast choke, and so this coil collapses, and the collapsing coil produces a very high voltage that we see at the electrodes, and that's enough voltage to strike across that gap there, and so that the lamp will come on. So we've got that explanation there. Heat up, glow switch contacts open, high voltage, blah blah blah, causes it to strike. So it's all about this glow starter opening, this choke collapsing, and us getting a high voltage on the electrodes. 2 purposes of the powder, the fluorescent powder. So it's to protect the eyes from harmful effects of UV rays and create the light color. And it also converts the UV light into visible light. So we need any 2 of those. This is a big question. It's a switchboard, low voltage electrical installation. We've got a number of criteria there, and you're asked to clearly show all of these things. Now with this question, I think it's just, and there's our one we're going to fill in, it's easiest just to wire this up how you would normally, and then look back at what they're asking, making sure you've covered everything. So we've got the main earth coming in to our earth bar, we've got our MEN connection, and we've got our main neutral coming in, and then we've got the neutral connections to the loads. We've got the water heater supply coming in, and that's coming to our main switch, and also the continuous supply to our main switch. The water is feeding through the main switch, through there, up to our water heater. So that would be a separately switched and protected supply. The continuous active supply again comes to our main switch, and then our main switch will feed our air conditioning and our range, and it will also feed our 2 RCDs. So we've got an RCD1 that's got a neutral connection there, and that's feeding our lighting and power one. And we've got RCD2, which also gets its feed from the main switch, and that feeds lighting 2 and power 2. And we've got our neutrals connected lighting and power through our neutral bars, our separate neutral bars. So it does look quite a scary question, but I think if you keep to the basics of how you wire the switchboard, then you can't go far wrong. Question 4. The MEN system, the loop through the main neutral conductor is typically of a lower impedance than the loop through the mass of Earth. Basically because this Earth neutral conductor is a solid copper, or it's a copper conductor, it's a continuous connection, whereas through the mass of Earth we're relying on the resistance of the Earth, the moisture in the Earth, to give us a low impedance, and typically that's not going to be as low as a permanently connected conductor. Now in this one, the main neutral conductor and the main earthing conductor are carrying similar currents. State the main reason why this situation would occur. So there's going to be something wrong with this neutral conductor if it's only carrying the same amount of current as that through the Earth. And what they're saying there is there's a high resistance joint in the main neutral conductor. Two factors that determine the level of prospective short circuit current in the installation. Again, we've seen this question before. It's all about the capacity of the supply, how much the kiloamps the supply can give out, the impedance of the earth fault loop, and the supply voltage. State 8 components of an MEN system that are found in an MEN low voltage electrical installation. So you need to know the MEN system. You need to be able to draw it and to describe it and to name the parts. So the main earth bar, main earthing conductor, earth electrode, MEN connection link, the main neutral bar, the main neutral conductor, protective earthing conductors, and the equipotential bonding conductors. So they are the components that will make up the MEN system. The main function of the main earthing conductor and the earth electrode in a low voltage MEN installation. So they give you a couple of answers there. Connect the parts of the installation required to be earthed to the mass of Earth, to keep the neutral potential to 0, and to keep the phase potential to 230 volts. So we've seen that question in a slightly different way, but the earthing is all about keeping that neutral at 0 and the phase at maximum of 230. Explain why class 2 double insulated is not required to have a protective earthing conductor. Well, we don't need it because there's supplementary insulation between the basic insulation, so that are the cables, and any metal that could become live under fault conditions. So there's another barrier after those cables. There's 2 parts of insulation. It makes it a class 2 double insulated. Question 5, we've got the components of a DOL. We've got L1, L2 and L3, and we've got our motor there, UVW. We've got our overload there and our overload contact there, some fuses and a contactor, and that contactor is going to control these 4 contacts. So these 3 are going to put our supply through to our motor, and this one is going to be our holding contact, and that holding contact is going to make sure that when we release the start switch, the motor will still go. It holds the supply to the motor. So how are we going to connect that up? We're going to have L1 is going to feed that fuse and feed the start button. Now I would have taken mine from the fuse straight to the start button there, and then the holding contact in parallel with the start. But it's exactly the same operation whether you take it there or there. So the main essence is that this holding contact is in parallel with this start button, and the stop button is in series. So we go through the circuit, through the stop, through this overload contact, to the coil, through the fuse, to the L3. So the control circuit is across 2 phases. It's across 400 volts there. If we press the start, we'll get the feed through to the coil. Close these contacts, motor starts, held in by this holding contact. Electronic starters are often used with three-phase AC induction motors. How the operation of an AC variable speed controller is different to electronic soft starter. Well, electronic soft starter is just all about the starting, as the name implies, and so it varies that voltage to limit the starting current, whereas the variable speed controller varies the frequency and the voltage to vary the speed. So when it's running, we can vary that frequency and voltage together, and we can change the speed of the motor. The ramp time of a variable speed controller, so that's the time that it takes for it to change in speed. So the adjustment that controls the length of time taken for a change in speed to take place. So how quickly it goes from one speed to the other. D, a 400 volt three-phase motor has got DOL. When started, the motor draws 90 amps and produces 200% full load torque. So 90 amps on a DOL. Calculate the starting current if the same motor is started with a star delta starter. So when it's by a DOL, it's as if it's starting in delta. When we start it in star, the current that it takes is a third of the DOL current. So this 90 amps would be reduced by a third if we was able to start it in star. And so here we've got I in star is the I in DOL times 0.33, which is the third. So 90 times 0.33 gives us 30 amps. There's the same motor, 200% full load torque. Calculate the percentage of starting torque if the same motor is started with an auto transformer starter with an 80% tap. Now this 80%, because we're only starting at 80% voltage, we're going to reduce this starting torque. And it's not going to be a direct reduction of 80%. It's that 80% squared times this 200. So it's the reduction in voltage squared as a, here we are at 0.8 as a decimal, so 80% is 0.8. 0.8 squared, which is 0.64, times the 200 gives us 128% full load torque. Wire rewirable fuses are classed as coarse excess current protection. So they're coarse excess current protection because they don't give us very close protection, basically. They've got a variable utilization category. So that fusing factor is not a determined value. It's very variable, and it's usually around about that 2 mark. So if we're talking about a 20 amp fuse, it's not going to blow at 20 amps, it's going to blow at 40 amps with that factor of 2, that fusing factor of 2. So it doesn't give very close protection. HRC fuses and MCB are close current protection. And why are they close current protection? Because their fusing factor, or the utilization category, is not more than 1.5. So they give us much closer protection. If it's a 10 amp fuse, we know it's going to blow before it gets to 15, or when it gets to 15. If it was a rewirable fuse, it might take until 20. So rewirable is coarse current protection, MCBs, GG HRC fuses, close. HRC fuses are used to provide short circuit and overload protection to three-phase motors. State the main reason why the HRC fuse do not provide overload protection. The HRC fuse is there really for short circuit protection. So it's able to break a very high current, and that's what it's there for, to provide short circuit protection. Apart from cost, state 2 technical advantages that HRC fuses have compared to MCBs. So one of those is that higher kiloamp rating, that higher short circuit protection, and it's also faster acting, so the speed of operation. Describe the term backup protection in relation to the protection of final subcircuits. So we would have another fuse in the circuit that would supplement the normal fuses in there, so, or an MCB. If there's an MCB, it won't have the rupturing capacity of the circuit maybe. So there'll be a high prospective short circuit current, and that MCB cannot handle that current, and so we put an HRC fuse in there, for instance, that backs up the MCB because that has the high rupturing capacity. So it's a protective device using an HRC fuse of adequate rupturing capacity in addition to the protective device of inadequate rupturing capacity. Term discrimination, so that's all about the protective device closest to the fault operating before any of the other protective devices. Question 7, we're going to transform a calculation. Three-phase delta star steps down from 33 kV to 11 kV at the output terminals. When fully loaded, a current of 15 amps flows in the primary windings, assuming no losses. So we're going to calculate the full load primary line current. Now we're told the phase primary current, because we've got 15 amp flows in the windings, so that's our phase current. Our line current is going to be √3 bigger than that phase current because we're connected in delta. So our line current is 15, which is our phase current, times √3, gives us just under 26 amps. Full load secondary line current, we're going to find the secondary phase voltage first. So the secondary phase voltage is going to be the line voltage, which is our 11 kV up here, divided by √3, and that will tell us the voltage across each of the phases in star. We've got a turns ratio of 33,000 to 6,351. So the turns ratio is all about the phase voltages. So there's our 33 of our delta, because the line and the phase are exactly the same, divided by our 6351 that we just calculated there, gives us 5.196 to 1. So that's the ratio between the windings and the voltages. The secondary line current is going to be the 15 amps times by this ratio. So there's our ratio, because if the voltage goes down by 5.196, the current is going to go up by 5.916. So the line current in the secondary is going to be 77.94 amps. We're asked to find the total kVA rating. So our kVA equation is √3 VL IL, and we can do this with either the primary or the secondary. So they've done it here with the primary. So √3, there's our primary line voltage, and there's our primary line current, and that gives us 1485 kVA. B, two methods used to cool transformers. So we can have a basic air-cooled, we can have oil-cooled, pumped or natural convection, or forced or natural ventilation. So if I was remembering those, I was just remembering air-cooled, oil-cooled. Label a circuit diagram of three-phase four-wave rectifier circuit supplied from a delta-delta supply transformer. So this comes up quite a lot, this three-phase rectifier. And there's our delta-delta, and there's our three-phase rectifier. So all the diodes pointing the same way, and then our line phase is there, just connected to 1, 2, 3. And now current is going to flow through the diode down, and then it will go back through the one that's connected to. So we're going to get a current flowing down here all the time, and these are all going to be conducting, and these are going to be conducting at different times, and that's going to give us 3 times 2 is going to give us 6 lumps, if you like, of DC per input. So what we've got now, we're going to explain the operation. So here we go there. Current flows from the most positive to the most negative line through one of the top diodes, the positives into the positives rail. So you need to label that as the positive. Through the load to the negative rail, there's a negative there, and back to the most negative line through the bottom diodes. So it will go out through the most positive and come back through the most negative. Draw and label the output waveform of one cycle. So there's our 1, 2, 3, 4, 5, 6 bumps of raw DC, and that's for one waveform input. State the output frequency. So if the input frequency is 50 Hertz, then we've now got 6 of these. So we're going to have 6 times 50 Hertz, which is going to give us 300 Hertz. Question 9, we've seen this one before, testing a voltage in front of a switch socket outlet, diddly-dee. So we've gone, the switch is off, so that's what we would expect. With the switch on, active to neutral, we'd expect 230 volts, but active to earth, we would expect 230 volts there, wouldn't we? Neutral to earth is okay, 0 volts. So why are we getting these readings? So we've either lost the protective earthing conductor, it's gone open circuit, there's no earth to the socket, the earth terminal is broken, or the MEN link is missing. We've installed a low voltage 3-phase 5-pin socket outlet and final sub-circuit in a bakery. It's not been connected to the switchboard yet, and we're going to do some testing, and we're got to do 3 tests. The only instrument you have is a multifunction meter with insulation resistance, so at least it tells us this time that we have got insulation resistance, 500 volts and 250 volts, and our basic other readings. So the first test we're going to do is an insulation resistance test, and the answer there, I would be tempted to do the protective earth conductor test first, but seems they've gone for insulation resistance. So insulation resistance function, 500 volts DC range. Testing between the phases, and we're going to make sure that between phase and neutral and each phase and earth, we've got 1 mega ohms or more. So you must remember that insulation resistance test, 500 volts DC, greater than 1 mega ohm. For our second test here, with the protective earthing conductor, so we're looking for resistance, a low ohms range. Test between the end of the protective earthing conductor at the unconnected end of the cable and the earth pin on the socket outlet. And we need a resistance that's low enough for the protection to operate in the required time. Test 3, we're looking at the circuit connections, making sure they're correct. Again, it's a low resistance range, and we're going to go between each conductor at the unconnected end of the cable and corresponding pin on the socket outlet. So there's a spelling mistake there. So we're just making sure that they're connected to the right end of the cable. And each correct result should show low ohms because it's going to be a continuous cable from one end to the other. So that's going to be our 3 tests, and that finishes that exam.